When you ask a question like, does this new program work or will this strategy succeed? The answer is almost never a simple yes or no. The real answer is usually, it depends. It depends on the situation, on the people involved. It's just common sense, right? But what's so weird is that for scientists, proving that simple it depends idea has been incredibly, frustratingly difficult.
So today, we're going to unpack this whole scientific detective story. We'll start with what I'm calling the it depends problem. Then we'll follow a massive 30-year investigation that looked into it. We'll cover its first major clue, a truly tiny effect, and then a huge twist called the power paradox. Finally, we'll see how this all forced researchers to rethink what small even means, and why these tiny discoveries actually matter a whole lot.
All right, so first, let's set the stage and really dig into this mystery that was bugging researchers for decades.
Imagine you ask a pretty straightforward question. Does a new training program improve employee performance? Well, the obvious answer is, it depends. Maybe it's a total game changer for your sales team, but for the engineers, it does absolutely nothing. The effect of that training depends on the group you're talking about.
Now, in science, this it depends factor has a fancy name. It's called a moderator effect. And researchers in fields like psychology and management, well, they expect to find these things everywhere. I mean, they're the foundation for theories about everything from what makes us happy at work to what makes a team click. Because let's face it, almost nothing in life is one size fits all.
But here is the big mystery. For years and years, study after study went looking for these common-sense moderator effects, and they came up empty. They just couldn't find them. This led to a huge crisis in these fields. Were all of their core theories just flat out wrong? Or was there something else going on entirely?
Well, to finally solve this puzzle, a team of researchers led by a guy named Herman McGinnis decided to launch this absolutely epic investigation.
And when I say epic, I mean it. This wasn't some small side project. They went back and analyzed 30 years of research, from 1969 all the way to 1998, digging through the most respected, top-tier journals in their field. Their thinking was, if these effects really exist, the evidence has to be in here somewhere.
Their whole investigation really boiled down to two key questions. Think of them like a detective at a crime scene. First, how big is the fingerprint? When you do find an effect, what's its size? And second, how good was the magnifying glass? In other words, how well equipped were these studies to even find the fingerprint to begin with? In science, we call that effect size and statistical power.
And that first clue they uncovered was, well, it was a bombshell. It seemed to solve the entire case, right on the spot.
So after combing through 3 decades of research, when scientists did manage to find one of these it depends effects, how big was it typically?
The typical effect size they observed using a measure called f², was a minuscule 0.002. That was the fingerprint left behind after all that time.
Now, to put that number in perspective, 0.002 isn't just small, it's practically microscopic. For years, the scientific rule of thumb said that an effect size of 0.02 was small. What they were actually finding was 10 times smaller than that. So case closed, right? The effects weren't being found because they were just too tiny to even matter?
But nope, the case wasn't closed, not even close, because then came the big twist in the story.
So the natural assumption here, the one everyone would make, is that the original studies just weren't powerful enough. The magnifying glass wasn't strong enough to see that microscopic fingerprint. Makes sense. But was it actually true? Not even a little bit. In a really shocking turn, the investigation found that 72% of the studies they looked at had more than enough power to find that conventional small effect of 0.02. So think about what that means. The researchers had basically brought high-powered telescopes to the crime scene, powerful enough to spot a distant planet, when what they really needed was a microscope. The tools they had were incredibly powerful, but they were calibrated for a target that was way too big. And this created a huge paradox. The problem wasn't a lack of power at all. It was a massive mismatch between what they expected to find and what was actually there. You can see it so clearly here. The studies had tons of power for the targets they were designed to find. I mean, the average power to detect an effect of 0.02 was a super strong 0.84. The tools were not the problem. The problem was that the targets were based on these old, flawed ideas about what small really meant. So this huge discovery that the effects were real, but tiny, and the scientific tools were powerful but miscalibrated, it forced the entire field to completely rethink how they do their work. The authors of the study said it perfectly. The issue wasn't the theories or even the methods, it was the expectations. As they put it here, researchers needed to start planning their studies for the world as it is, not the world as they thought it was.
And all this led to a brand new playbook for scientists. Step 1, clean up your data. Be aware of things like measurement errors that can hide or shrink in effect. Step 2, throw out the old rulebook. Stop using those outdated labels for small, medium, and large. And step 3, maybe the most important, be realistic. Plan your research to find smaller effects that can still be incredibly meaningful.
Now, I know this all might sound a little bit academic, but a so-called tiny effect can have an absolutely enormous impact in the real world.
Just think about a tiny bias in performance reviews. Let's say it accounts for just a 1% difference in the scores between men and women. In any single study, an effect that small would be almost impossible to even find. You just dismiss it as statistical noise.
1%. Seems like nothing, right? Almost meaningless. But what happens when that tiny, almost invisible 1% bias gets applied over and over and over again, year after year, promotion after promotion, across an entire company? Well, that effect starts to compound. And this is the result. A simulation of this exact scenario found that a persistent 1% bias eventually leads to a situation where women hold only 35% of the top leadership jobs. That tiny, almost undetectable effect, once it compounds over time, creates a huge, tangible disparity that you can see and feel.
So what this 30-year investigation really showed us is a fundamental truth about discovery. The search for knowledge isn't always about finding some huge, dramatic, earth-shattering effect. Sometimes the most important discoveries, the ones with the biggest consequences, are small, persistent, and hiding in plain sight. Which leaves us with a really big question. What other tiny effects are quietly shaping our world right now, just waiting for us to finally use the right tools to see them?